Welcome. In this podcast, we're going to learn about some features of polynomial functions. All right, the first thing we're going to learn about are turning points. That's where the graph of a function changes from increasing to decreasing or vice versa. So I put a little TP there next to turning point so that I could show you on the graph where there is a turning point. And since I don't have enough space there to write turning point, I can just put TP. So TP stands for turning point, not toilet paper. Right, so right here, and so I'm going to mark them on both graphs. Right, so there's a turning point right there on that graph. There's a turning point right here, at that point right there. So actually, I'll darken them so you can see them. And there's a turning point right here. If we go to the other graph, there's a turning point right here. And another one right here. So one graph has 3 turning points and the other one has 2 turning points. There are 2 different kinds of turning points. There is a local maximum and a local minimum. Right? So there are actually 2 names for each of those. I could call them a local maximum, or I could call it a relative maximum. They mean the exact same thing. I tend to use relative maximum over local, right? But either is correct and they have the same meaning. Right? So when we're saying local, we mean that we're just looking at a section of the graph, not the entire graph. If we were looking at the entire graph, I'll write the word in. So we have local, relative, and we have another word called global. Right? And I will put it on top because I have no other space. So it'd be good for you to know. And so actually on your notes, you have this page. Just add this little part to it. And by the way, you can add the TP there for toilet paper. Nah, turning point. So global means the entire graph. And for polynomials, that would mean from negative infinity to infinity. Okay? Not the entire graph we see. The entire graph over its domain. Right? So the entire graph over its entire domain, that's global. If we say relative or local, right, that's going to be, it's going to refer to a section of the graph. Right? So both relative and local, they mean a section of the graph, and whereas global means the entire graph over its entire domain, not just what you can see. Because there's no way we can generally, if we're talking polynomials, there's no way we can draw the entire graph because its domain is infinite. And so we would never be done. Right? So there's a little difference there between global and relative. And so let me actually show you what that means. And this is the first time I'm trying this on a podcast. And that is, I'm going to try a device called, Spotlight. And now your screen should be all black, right? Except for a circle in the middle there. And actually my circle's too big. So I'm going to make it smaller. And I have to tell you that I am not extremely good at making my circle smaller. There we go. Whoops. And it doesn't matter if it turns to an oval, which is good because that's probably what's going to happen. All right. Now I'm going to move my circle. I think if I pull this thing. There we go. All right. So if we're referring to local or relative maximum, I'm looking at a small section of the graph, and I'm looking for the part that is the highest, the largest value in that particular section. Right, so if you notice there, right, see where it says TP, and we see we have a little hill here. I can't write, I guess I could write in that little section, but I'll just use my mouse here. All right, so that little point there, that point, that is a relative maximum because that would be a high point on my graph. Right? It's relative to the other points in this little section of the graph. That is the largest point. Right? So that is a relative maximum. So there's our relative maximum. Oops, I didn't want to change the size, I just want to move it. Let's look for other relative values, other local values. Actually, what we're looking for is actually local extrema. Oh, there's one, but I need to make my circle a little bit smaller because it's getting a couple in there. So let me just make that a little bit smaller. There we go. All right, you see that point right there? We see TP. All right, notice that is the smallest value in this little section of the graph. That is another relative extrema. That's a relative minimum, because that's the lowest value in a section of the graph. And I have to remember not to move my screen by the edges. I got to go to this little whatever this thing is next to it. And here we have one more turning point. And if I move it up a little bit, you can see the words TP. Right? And so we have a relative maximum there. Notice that if we look at this section of the graph, that is the highest, the little peak there. That's the highest value in that section of the graph. Let's do the same thing and go to the other graph. So we're moving there. So we see our little TP there. All right, here we have another turning point. Is it a relative max or a relative min? Well, notice that my graph is increasing, right? It's going up. And then I get to this point and I turn around and I go the other way. Right? So this is a relative max. It's the largest value in this section. And we had one other turning point. Oops, stop that. And that was our other turning point. There's TP. Right? And see, we're decreasing and then we're increasing. We're turning around and increasing. That is a relative minimum. Right? It's the lowest value in this section of the graph. So your relative max and relative min values are always occur at turning points. Right? Those are turning points to your graph. Right? And whether you're a relative maximum or a relative minimum just depends. Are you the lowest value? Was the graph decreasing and then it turned around and you're increasing? Then you're a relative minimum. If instead the graph was increasing and then it turned around and started decreasing, you're a relative maximum. So there's a relative maximum, and that's what a relative minimum looks like. And let's get rid of the screen shade now. So you have to tell me what you, not screen shade, spotlight. You have to tell me what you think of the spotlight. And try to use that feature a little bit more. All right, so we talked about our relative maximum and relative minimum, or a local maximum and local minimum. So a local maximum, or relative maximum, is the highest point or peak in an interval. Function values at these points are called local maximum or relative maximum. And then local minimum, lowest point or value in an interval. Function values at these points are called local minimum or relative minimum. So if we look at our two graphs here, and on graph number 1, you see we have P1, point 1, point 2, and point 3. Well, point 1 and point 2, those are local maximums. Right? Those were the highest values in the section of the graph, right? When we were doing a little spotlight there. It went increasing and then decreasing, right? So that's a local maximum. Point 3 there, that's a local minimum. Right? We were decreasing and then we're increasing. I already wrote, and it's already in your notes, that increasing and decreasing part. Right? So increasing and decreasing, remember we read graphs left to right, so it depends. Is your graph going up? If you read left to right, that's increasing. So that would be increasing, this would be increasing. Or does your graph go down as you read it left to right? So this would be decreasing, this would be decreasing. We are going to spend an entire podcast talking just about, well, not just about, but mostly about increasing and decreasing, right? So that's just a little introduction. So I'll do it on both graphs, right? So there's the blue is the increasing and the green is the decreasing. And so here, as I read left to right, my graph is going up, right? That's my increasing. Also over here, as I read left to right, my graph is going up. That would be increasing. And then right here where my graph is going down, that's decreasing. And I believe everything is in your notes already for this. Right? So if we look at, let's look at graph 2. Right? So point 1 there, that is a local maximum because our graph went from increasing and then to decreasing. And point 2 is a local minimum because we went from decreasing to increasing. But we're getting a lot of content in one page. I'm at 9 minutes already. So if I wanted to state where my graph was increasing or decreasing, remember it's the x values, not the y values. I have this on your notes already. You might want to put a little star on this page because there's a lot of content on here so that you can remember to refer back to this if you have a question. And if you forget, like, oh, what am I supposed to do when I'm asked, where is it increasing, where is it decreasing? So where is x? All right, so for the graph on the left there, our graph is increasing from negative infinity till it gets to 0.1, right? And here's my turning point. I'll just make my point darker so you can see where I'm talking about. Right? And then my graph is also increasing from 0.3, right? So if I want to say 0.1, I use the x value. So my x value for 0.1 is x1. So it's increasing from negative infinity to x1. And so this is where I am. And then it's increasing again from x3, right? Because it's the x values, up to, that's hard to draw under this one, but to x2, right? So that's where my graph was increasing, where you see the blue, and it's the x values we give. My graph was decreasing from x1, right? So after it increased, it had to decrease from x1 to x3, and then again from x2, yeah, I can get a green line in there, there we go, and then forever, right? So it's going to keep decreasing forever and ever, and so that would be infinity. Right? It does not matter if the graph is pointing down, that is not negative infinity, because it's the y values that are decreasing, the y values that, the y values are getting smaller. That's what makes the graph decreasing. But the x values are going to just keep on going forever and ever. That graph will get wider forever and ever and ever. If we look at the second graph there, right, so it's going to be increasing from negative infinity, right? So as we look to the left, so from the beginning of time, all the way from negative infinity, until it gets to this point here, x1, my graph is increasing. It starts increasing again at x2, and it keeps on increasing forever and ever and ever. Right? It doesn't matter which way the graph is pointing, up or down, right? Because the where is it increasing is referring to x, and x is going to go across the entire domain, for polynomials anyway. And I underlined with the wrong pen because, remember, the blue was increasing. There we go, we'll just fix that. Right? And then it's decreasing just between x1 and x2, that's it. Right? So let's look what other information I have on this. So we talked about increasing, decreasing. We talked about turning points. We talked about relative maximums and relative minimums. And the last thing I'm going to talk about is degree and leading coefficient and how I knew which was which. Right? So, and I'm actually going to tell you how I knew it was degree 4 as opposed to degree 2 or degree 6. Right? But we can definitely tell the graph on the left here. Let's call it graph number 1. We can definitely tell that that one is an even. Why would it have to be an even degree? Notice both ends are facing the same direction. That only happens for an even graph. You can also say, oh, it's got a W shape, and W shape is an even graph. I will tell you how I know it's fourth power in a moment. The leading coefficient is negative, and we know because it's concave, well, I can't say concave down. We know because the ends are pointing down, right? They're going to negative infinity. In terms of concave up and concave down, different portions of our graph are concave up or concave down. Just as this is kind of an extra. This is bonus, since I just said concave. I had to be careful with polynomials because it's not quite the same for all polynomials as it is as quadratics. So here, that section there, that is all concave down. Right? That's the concave down section. If that were a cup, all your water is falling out. The concave up section is right over here. That's all concave up. So I'll just add that in there. So I will tell you it's optional. If you want a little extra information, that'll come in handy in the later classes. This part here, so between x1 and x2, where it looks like the cup would hold water, that's concave up. Where it looks like all the water would fall out, I should not really write in green over green. This would be concave down. Okay, so here and here. And I don't even know if you can read that. Well, I told you it said concave, so you'll have to trust me. It says concave. All right, so that's just a little extra information. All right, so we were talking about leading coefficient being negative. Right, since both ends are going towards negative infinity, they're going down. What's down? Right, down is negative infinity. That means the leading coefficient has to be negative. If we look at graph number 2, right, on graph number 2, we're odd because the two ends are going different directions, right? One is going down, one's going up. It has to be an odd function. I know the leading coefficient is positive because it goes up left to right. If it goes up left to right, like a linear function, the slope is positive if it goes up left to right. Polynomials also got a leading coefficient that's positive if the graph goes up left to right. And when we say up left to right, it means as we go from here to here, not the in-betweens. We're looking at the end behaviors, right? So overall, from one section to the other, it's going across the whole graph, it's going up left to right. All right, so the only thing we have to talk about is how did I know that one was 4th degree and the other was 3rd degree? And I inadvertently left this out of your notes. Terrible me. So we're going to add a page, and it won't take me very long, or very much space, right? So just find a little page, a little place in your notes, or a sticky note, right? So I will tell you that, and so we're going to call this degree of polynomial function. All right. So degree, both these are true for both of them. I'm going to leave out degree 0, okay? We're going to start with degree 1. Degree 1 has 0 turning points. Remember what degree 1 looks like? It's a line. Degree 2 has, now I'm going to use the words at most, 1 turning point. It's hard to say at most with 0, I guess, but. Right, and remember degree 2 looks like this, parabola, or it could be the other way, but I'm just going to draw 1 for each of these. Degree 3 has at most 2. Turning points. And degree 3, I'll just draw a generic one. It could go the other direction, but we'll just draw it going that way. Degree 4 has at most 3 turning points. And it looks like degree, I'm just going to draw one type. I'm not going to draw the upside down one too. It would look like that, right? Basically looks like that shape. Right, so look at the numbers and let's see if you could figure out how I figured out the degree. And let's go back to that other graph. And let's count. All right, we're looking at graph number 1, right? And how many turning points were there? There is 1, 2, 3 turning points. So I knew it was 4th degree or 4th power. I'm going to use the word degree. Although 4th degree means there's an x to the 4th. So let's write both things in. Don't worry that yours says power, it's fine. But next to it, let's just put an x to the 4th. Let's count the turning points again. So we have 1, 2. Those turning points are getting really big as I keep drawing over them. We have 2 turning points. And this is 3rd degree, which is x cubed. Have you figured out how I knew one was 4th and the other was 3rd? Let's go back to our little table here. And if you write nothing else, I want you to write this. Right, so this would be very helpful, the stuff above, but this is absolutely crucial to go in the notes. Right? So degree n has at most n minus 1 turning points. So notice 0 turning points, degree 1. 1 turning point, degree 2. 2 turning points, degree 3. 3 turning points, degree 4. N minus 1, degree n. So there's going to be 1 less turning point than degree. So I'll write it 2 different ways. So I'll say the turning points, I'll just actually write it one way. Turning points is 1 less than the degree. I guess I'll write it 2 ways. The other way you could think about it is, or degree is 1 more than turning point. However you think that's easier to remember. So I just counted the number of turning points. I knew basically, we knew that. Oh, and if you need to write this down, just pause me. And we knew that this has to be even, right, because the ends are going the same way. And since there's 3 turning points, it has to be degree 4. The other one, ends are going different ways, has to be odd. There's 2 turning points, it has to be 3rd degree. So that's how I can tell that one was 4th and not 6th or 8th, and the other was 3rd and not 5th or 7th. Now, if you notice, there was that word at least. So why did I say at least? Or excuse me, at most. Why did I say at most? Well, we'll talk about why there's at most. There could be less. So, of course, you can't be less than 0. So that's why I didn't put at most. And actually, I really can't be, because I'm not going to have 0. So I will tell you that this one always has 1 turning point. Okay? And I cannot move that over for some reason. So I really did not need the word at most here. Sorry if you wrote the word at most. I don't necessarily need the word at most there because it will have 1 turning point. But sometimes it might be that our graphs, degree 3 and higher, don't have 2 turning points or 3 turning points or whatever turning points. And we'll talk about why that might occur in a later podcast. The last thing I'm going to say, I was going to make this all 1 podcast. This is going to have to be 2 podcasts. This whole thing I took a whole podcast on. But don't worry, on the next podcast, I can go a lot faster because I've told you what all these things mean. The other thing I wanted to say, and it was in your notes, but I did not mention it when I was going over the intervals for decreasing and increasing. So in math, we like abbreviations so that we can write things more succinctly. And so rather than writing the word and, we use the U, and the U means union, right? So union just means both of these things, this and that, right? So where it's increasing, it's negative infinity to x1 and x3 to x2, right? So that's what that means. In the next podcast, we are going to identify features of polynomial functions, maximums, minimums, x-intercepts, y-intercepts, all that good stuff. And we're going to do that from a graph. So come back to the next podcast. Bye for now.